Recording. There we go. And now we are recording. Maybe some of your friends, colleagues will join later. That's not a problem. They can join anytime. So welcome everyone to a webinar, my first one actually. And today we're gonna be briefly going through binary search trees and their implementation in C. Now, I have to change something. There we go. Can you see my paint thingy?
Yes.
Great. Okay, so a binary search tree is basically a tree in which all the nodes of the leftmost subtree are smaller than the root. So let's assume that this 5 is a root. So all the nodes on the leftmost subtree are going to be smaller than 5, actually contain a value which is smaller than 5. And all of the rightmost nodes in the right subtree will be larger. So in order to have that, let's just fill it up. So this should be a 4, this should be a 3, this should be a 1, and this is going to be a 4.5. And here, let's put a 9, a 7, and a 11. Now let's see if that thing still holds. Every subtree must be, every left subtree must have values smaller than, just smaller than, not equal, just smaller than the root. So if we take this one, all the values here are smaller than 5. And for example, this one, all the values here are smaller than 4. And let's take the rightmost ones. All the values here are larger than 5, but 7 is smaller than 9 because it's on the left subtree of 9, and 11 is larger than 9, and so on and so forth. And this is basically a binary search tree. Now, can anyone tell me, by looking at this, what would be the efficiency or, basically the complexity of searching for a node in a binary search tree? Don't be shy.
N.
I'm sorry, a bit louder.
The logarithm in base 2 of
Yes, the logarithm in base 2 of n. And do you know why?
Because for each step we are going onto another level in the tree. So we have log 2 of n levels for the tree, so and elements and nodes.
Exactly. So for the value of n, regardless of how big n is, the height of the tree, which is h, is always going to be logarithm of n. Log of n. So that's the maximum value of the height of the tree. And that's why in a perfectly balanced binary search tree, the search will always take just log of n. However, there is a catch. What I described here is a perfectly balanced tree. However, if I were to do this, for example, and I think that's enough. No, actually I need one more. So if I were to do this and add 2 more elements here, and let's say one of them is 0 and the other one is -5. What happened here? Do I still have, first of all, a binary search tree based on the rules I talked about previously? Yes or no? Don't be shy. Just unmute and say yes or no. Is this still a binary search tree? Anyone?
Yes.
Yes, it is. But then what is the complexity of finding -5, for example, is it still a maximum of logarithm of n?
No.
No, it's not, because there is something, a kind of a rule which I broke here, but it's not a rule for general binary search trees. It's actually a rule for perfectly balanced binary search trees. And the difference between a perfectly balanced binary search tree and just a normal binary search tree is that the perfectly balanced one has an additional rule which states that the height of the left subtree must be at most one higher or lower than the height of the left of the right subtree. So, and this applies to all the subtrees of the nodes. So, for example, the height of this subtree over here, and I'm gonna circle it. The height of this subtree, starting from 4, is what? Come on, give me an answer.
4.
It's well, actually, I think it's 5. But yeah, I guess if you count from height 0, yes, it's 4. And then the height of this is
2.
2. So there we have our problem. The left subtree of 5 has the height 5 or 4, and this one has the height, well, 1 or 2, I guess, but let's just put it 2. And here, because it's the height of the rightmost subtree is 2 lower than the height of the left subtree, or 3 actually lower, we have an imbalanced tree. And because this is an imbalanced tree, the height of it cannot be just log of n, and so the search doesn't execute in log of n. Okay, so this was just the theory. For starters, we will implement a binary search tree which is not perfectly balanced. So this is what we're going to implement during the lab right now. And homework, you're going to have to implement a binary search tree which is actually perfectly balanced as well. At least the assignment, which is obligatory, will be will have you implement the insertion of a node in a perfectly balanced tree. And then the extra assignment will also have the deletion of that node. And you'll have to respect each time you insert or delete these extra restrictions, basically the height, which has to stay at most with at most one difference for each subtree, left and right. Okay, now I'm gonna switch to my editor, and that's gonna be this. Okay, so now you can see my editor, right?
Yes.
Thank you, finally. All right, so let's start off. I have already implemented a few things just so we can spare some time. First off, I have my structure, which just the same as before with our tree from last time, has a left and right node and a key. And I've also implemented a pretty print function over here, which will just print my tree. And that's about it. That's all I have implemented. Everything else will be writing from scratch right now. All right. So let's start off with creating our root node. Oh, and I have to actually include this. No. Yeah, there we go. So equals to create node of, and let's just give it a key 10. All right, so I'm gonna need to create this function, create node, and I'm gonna put the name of this parameter key and put it below. There we go. Okay. So here I just need to allocate some space. Oopsie. And I'm gonna have it point left to null and right to null. Oh, and here I need this. Oh, and by the way, if you don't understand something and I'm missing something, maybe stop me at any time. You don't have to raise your hand or anything. Just stop me, interrupt me, whatever. I don't mind. And I'm gonna need to assign the key and finally return the node. Okay, and I'm gonna reuse this function more than once, I assume. And here, let's just write a few insert statements. So insert root to, and let's just put 9. And I'm gonna need to create this function insert. And this is gonna be the root. And insert a key. Okay, now, I don't wanna have a variable, a global variable floating around the root. And that's why I'm passing it to the function as a parameter. Otherwise, if you would have this root variable somewhere here maybe, or at the top as a global variable, you won't need to pass it as a parameter. I don't very much like global variables, and that's why I keep passing them through function parameters. Okay, and I'm gonna have to do this. And this is gonna be my new node, which I wanna insert. And instead of 10, I'm gonna put key. Okay, so in case I don't have a root anymore, actually, in case I don't have a root here, if root is equal to null, I'm gonna just return my new node. And this insert will not be a void, will actually be a node T. And I'm gonna change that here as well. Okay. Any ideas on what I should be doing here? Is anyone courageous enough to help me out? Guess not. Boy, you're a tough crowd. All right, so I will need to iterate a bit through this through my tree here, and let me show you what I have in mind. Let's go back to our paint example. So assume we have this tree already, and I want to insert the key, actually not 9, let's insert 8. I want to insert 8, and 8 will be inserted logically here on the right side of 7. Am I right? Because it's smaller than 9 and it's bigger than 7, so it's on the left subtree of 9, but on the right subtree of 7. So let's create a node there. There we go. And then fill this and put 8 here. Now, the logic behind this insertion is simply if the key I'm wanting to insert is larger than the current node I'm at, then I go to the right subtree of that current node. If it's smaller, I go to the left subtree until I reach a null. When I reach a null, I know that I can insert it in that position and make the proper links. Okay? Is everything clear? Can I go forward?
Yes.
Thank you. If anyone has any questions, just tell me. Okay, so back to our editor. I'm gonna need to iterate through my tree, and for that I'll need an auxiliary variable called aux, whatever. And I'm gonna need a for loop, and you can do this with a while loop as well. It doesn't really matter. And I'm gonna return and exit this for loop when I'm done in each case. So I don't need to know how many times this executes. So that's why I can also do this while true. Well, of course, it gives me, oh, come on. There we go. but let's just leave it with a for loop. So if the key I want to insert is smaller than aux key, so this is my current root, then I have two cases here. If, first off, the left subtree, the left node of aux is null, then what does this mean? Anyone?
We
Come on.
should add it there.
Exactly. I found the position where I want to insert it. And I'm going to put aux of left equals to node and return node. Okay? And if not, else. If not, then what should I be doing? Remember, I'm here in the case in which key is smaller than the current node I'm at, key. Anyone?
We should keep looking on the left side of the tree.
Exactly. And how do I do that? How do I move forward on the left side of my tree?
We call the insertion function again for root of left.
I would rather not make this recursive. I know what you mean. Let's save that recursion for delete because I already created my node. I don't need to call it recursively and create another one as well. But I know what you mean. It can be done recursively, and we are going to do that for our delete function. But for the sake of simplicity, let's assume that this is an iterative approach, not a recursive one. So what other option do I have?
We just move aux into aux left.
Yes.
And then do it again in the for loop.
Exactly. So that's about it here. Okay. Else, if key is actually bigger than aux of key, then I have, again, two cases. If aux of right is equal to null, then what?
We insert it again.
Yes, exactly. So aux of right equals to node and return a node. Otherwise, then we need to keep searching on the right side of my tree. So else aux equals to aux of right. And I have another case here. Can anyone tell me which one that is?
If they are equal.
If they are equal. So if I already have the key in the tree, this is a very special case because binary search trees normally cannot have the same key twice. It would kind of defeat the purpose. So printf key, oops, already in the tree. And here I put tree. And again, remember to free up some memory when you have to. We're going to free up the node and return null because we didn't really insert anything. Okay, so let's test this insert function and see how it behaves and if it works properly. And I'm going to insert a few more things. So let's insert 8 and then 9 and then 2 and then 4 and then 5 and then 1 and 2 and 0. And then pretty print our tree like this. Okay. So what did I do here? And what can you notice? And you have to turn your head a bit, I know. Anyone? This tree has a very special particularity, which is tough crowd. Come on, tell me. Right. Anyone? Really? Can you at least still hear me, by the way?
We can.
Is anyone actually paying attention?
Yes.
Yes, great. Then tell me what the particularity of this tree is. It has all its nodes on the left side of it, right? Because everything is smaller than 10. Okay, let's insert a few more things. So 15 maybe, and then 13, and then 18 and 17, and then print. See what we get. Finally, so we have 10 our root, which just sits somewhere in the middle and on the first column. And then we have 8 and 15, which are on the same column. So they are the root of 10's left and right subtree. And then there's a 9 on the right subtree of 8, and so on and so forth. And yeah, this is my tree. Looks pretty good. Do you have any questions for our insert function? Or is everything clear? I will assume everything is clear. So then let's jump to our find function. So we're gonna find, actually I'm gonna write a function called find with print, and you'll see why. And let's assume we wanna find 0 and create this new function. Name this variable parameter root and this one key. Oh, bummer. Okay, so apparently our meeting will end in 10 minutes. I am gonna give you a new link, which I'll kindly ask you to join in 10 minutes. All right, so this find with print is actually gonna look like this. If our proper find function is gonna return a true, then printf key found in tree, and then a new line. Oops. Else I'm gonna print that the key was not found. And yeah, this find function, I'm gonna finally implement it. Okay. Any ideas on what I should be doing here? And this is gonna be a recursive function, by the way. All right, I'm guessing you're not gonna help all that much. So if the root of the function if the root parameter is null, that means I did not find it, and I can simply return false. And going further, else, if the key of the root is equal to the key, that means I did find my value, so I'm gonna return true. Else, in case I didn't find it just yet, but I did not reach a leaf, which a leaf node or a null, then I do a check. If my key is smaller than root of key, then the key of the root, then I will return find of root of left and key. Else, the same thing, but a bit different. I'm gonna search on the right. And I don't need this. Questions? Is everything clear? Yep, okay. So let's try it out a bit. So find with print, and I'm gonna search for 0, actually root and 0. That's okay, and 1 and 4 and 6 and 5. I don't know which ones I have, but that doesn't really matter. And I think here I'll need a new line. All right, so key 0 was found in the tree, and it's over here. Key 2 was also found. Key 4 was also found. Key 6 is not found because I didn't put it yet. And key 5 is also in the tree, and it is over here. All right, so the find function works properly. But does everyone understand the recursive part of all this? Is it clear to everyone? Why here I return find of left of the left subtree and find of the right subtree here?
Yes.
Great. Okay. Now let's take a 2-minute break in which I will provide the new Zoom link for you and then come back and finish up with our delete function. And that's maybe going to be a bit more difficult to understand, but yeah, 2-minute break and then we'll be back. Alrighty, so the only thing we have left now is the delete function, and that will be fairly similar to our insert combined with find. So let's just write this: delete a root, and let's just delete 4. All right. There's a catch here, and you'll see what I mean by that. Root and key. Okay. Now, first off, if our root is null, then we just return root, or return null. It doesn't really matter. We can't do anything. You'll see what I mean by this and why this is needed. Now, if, however, the key I'm looking for to delete is smaller than the key which hides in our current root, then the left subtree of my root will be equal to delete of root of left and key. Otherwise, if the key I'm looking for is bigger than the root key, then the right subtree, root of right, is going to be equal to the delete function of the root, right, and key. Okay. Are you with me so far?
Yeah.
Yes.
Okay. All right. Otherwise, I have 2 cases which I want to cover here. If the left subtree of my root is equal to null, then I am going to need a temporary variable, and let's just name it temp. And that's going to be the right subtree of my root. And I'm going to free my root and return this temporary variable. Okay, so what happened here? Can anyone tell me? First off,
I'm sorry to interrupt, but our Erasmus colleague is trying to join this meeting, but it says that he has to enter a password. I don't know why.
I honestly don't know why either. Did you give him the link I just sent you?
Yes,
I had the same problem, and the problem was there only if I tried to log in from the Zoom application, but if I open the link in my web browser, then it worked all right, and and the password wasn't required.
Yeah, that should be exactly.
All right, I'm telling him now.
Please do.
Thank you.
So yeah, no, don't worry about it. In which case am I here, first of all? What is this else?
When the key of the element we want to delete is equal to the key of the root, the current root.
Yes, exactly. Okay, what else? What is this if? Or how can you translate this in normal terms?
It's trying to find that if the left child of root is, no, if the root is a leaf.
Yeah, no, not really. Not necessarily a leaf.
Then it doesn't. If it tries to find if it doesn't have a left child.
Yes, exactly. And I'll show you in Paint what I mean by that. So let's assume that we want to delete 7. Okay, so we are here. So we started at 5, and let me just copy this code and see if we can think about it in parallel and put it here. So we started at 5 because our root node was 5 and we want to delete 7. Okay, well, the root is not null, clearly, because it's 5. So we pass this first, there we go. We pass this and go on here. And key is not smaller than root of key because I'm trying to delete 7. So we enter this clause over here because key is indeed bigger than the key of the root, which is 5. So 7 is bigger than 5. And that means that the root of right is going to equal to delete of the root of the right subtree of the right subtree of the root and key. So what is going on here? I enter this delete again. And what is going to be my root? The second time around, 9, exactly. So once I enter here, the root is 9. Okay, again, root is not null, that fails. Is the key smaller than 9?
Yes.
Yes, it is, because I'm trying to delete 7, and 7 is smaller than 9. So that means I go into this branch and end up here again. What is root?
7.
7, yes, great. Does it go on this branch?
No.
Does it go on this branch?
No.
Does it go on this branch then?
Yes.
Yes, finally. And does it go here?
Yes.
Yes, it does, because our left subtree is actually a null. And now 7 is not a leaf because it has a child. It has a child, and that child is 8. So what I do here is I create a temporary variable called temp, and I assign it to the right subtree of 7. And you know, this subtree could have been bigger. We could have had another element here, and it could have been 8.5, right? Okay, great. Now, what this does is assign that to a temporary variable. We free the root, which is what here?
7.
Which is 7. And then we return this temporary variable. And where exactly do we end up when returning this?
In root of left.
Here, right?
Yes.
Yes. And what is going on here? What happens next?
Well, basically 9 will now point to 8.
Exactly. So let's try to somehow delete all this. Oh, bummer. Next time I'll be sure to use Photoshop, honestly. Ugh. No, what is going on? Here we go. So we delete all this and yeah. And oh, bummer. Okay. That's a bad idea. But we'll make it work somehow. Okay, and this is what actually happens there. The left subtree of 9 is now 8 because we deleted 7. Is it clear why this happened?
Yeah.
Yes.
Okay, awesome. Great. Then let's go back to our initial state and implement a bit more code. New share and here. Now you can see my editor, right?
Yeah.
Okay, we're gonna have to do kind of the same thing, but in case we have a null right subtree, so else if root of right is equal to null, then basically pretty much the same thing, but in mirrored. And instead of getting the right subtree, we get the left subtree. We free up root and then return that new left subtree. Else, what is here? What is this case? We don't even need an else here. We can just write our code.
We have a terminal leaf.
Do we? Really? Pretty sure we don't.
I think we have in the middle a node or somewhere.
What do you mean in the middle?
Both left and the right child.
Yes.
Yes.
So we have both a left and a right child. Now let's take a look at that picture again and see how we can treat this case. So picking up, let's say, node number 4, okay? And let's make this a bit more complicated because now it is a bit too simple. Here and add a few more nodes here. God damn it. Okay, great. And here I'm going to have a 2, and here I'm going to have a 4.25, I guess. And here I'm going to have a 4.75. All right, so assuming we want to delete 4, intuitively...
2 is okay there.
No, it's not. You're right. This is really...
3.5 maybe.
Yep, yeah, you are right. Let me just correct this. There we go, cover it up, and then put a 3.5. Yes, thank you. Okay, so assuming we want to delete 4, how would we go around that?
We have to compare 3 with 4.5 and put there I don't know, the smallest maybe.
What do you mean?
I think we should put there 4.5 and then connect 3 with 4.5.
Okay, so you would want to put here instead of 4, a 4.5. So you have 4.5 here. And then what happens to these things over here? Whoops. What happens to these two?
We should put the whole tree, not just 4.5, the tree that has the 4.5 root.
Okay, then assuming you do that, what happens to this subtree? Because 4.5 already has 2 children, right? Then you would need to put a third child and somehow put this left subtree of what was previously 4 as a child of 4.5. Is that correct? So how do you treat that case?
Yes, I think it's not a child of 4.5. Actually, I think it's a child of 4.25. And that should be the correct tree resulted from the relation.
Yes, that would be the correct result. But that's also a bit more complicated to write because you would have quite a few different cases. For example, what if this 4.5 didn't have a left subtree? Well, then I guess it's simple. We just switch around. But what if, I don't know.
What if 4.25 has another left child, like 4.1?
Yeah.
That's the problem.
That's, so like, for example, here, what if we had, and it's going to be 4.12, for example. What if we had this? What then?
You should first put the subtree with the root tree in an auxiliary tree node, and then move 4.5 in the place of 4, then search from the child of 4.5 until child is smaller than 3, and then replaced it, and so on till we've
that sounds very, very complicated.
Yeah.
Mm-hmm. Now, I'm going to give you a small hint. Are there any nodes which can simply replace 4 without having to change anything else?
The node in the right side.
Which one?
4.5.
So if 4.5, if we just switch this around, then we would have the same problem because we would somehow need to treat this complex thing here. Whoa, crap. We would somehow need to treat this subtree. And that's not ideal. That's not what we want. My question is, and I'm putting it a bit more clearly, is there any node we can just take and put it instead of 4 and then change nothing?
The leftmost node in the right subtree, or if it doesn't exist, then the rightmost node in the left subtree.
Yes, exactly. And those are called predecessors or successors. So let's define these two. A predecessor, and think about it logically, a predecessor is some node which is right before our current node in value. Okay? So which node in any subtree, which node would be the closest one in value to the current root? Question. And I need your answer. So for example, let's take 5, right? Which is the predecessor of 5?
The leftmost child of the right child?
No, that's the successor. That's
okay, so then the
yeah,
rightmost child of the left child.
Exactly. So let's go through this again. The predecessor, so pre stands for something that is before, predecessor. It's like saying the one which is right before our current root, and let's assume that's a 5, is the biggest node from the left subtree. Is that correct? Because it's surely smaller than 5, so it precedes 5, but it has to be the biggest value because I want it to be the closest one to 5. That's what makes it predecessor, the predecessor. And which is the predecessor of 5?
4.75.
Exactly. So the rightmost node in the left subtree, and I'm gonna actually write that. So predecessor equal rightmost node in left subtree, and successor is the leftmost node in the right subtree. And let's see which node is the predecessor of 5. Actually, I'm sorry, the successor of 5. Which node is the successor of 5?
7.
Yes. Now, what if I put this here? God damn it. Please change color for fuck's sake. Finally. What if I put another node here and let's just put 8? Is 7 still the predecessor, the successor of 5?
Yes.
Yes.
Why?
Because 8 is not the leftmost node in the right subtree.
Yes, correct. Correct. So, what is the predecessor of 4?
3.5.
And what is the successor of 4?
4.12.
Yes. Now, regardless of which one we chose here, we can simply replace 4 with any one of them, and everything else can stay the same. Let me prove it to you. Let's say we delete 4 and replace it with its predecessor, which was 3.5. And we can have 3.5 and delete what was previously 3.5. So this one. And that's it. I don't need to do anything else. Is that correct?
Yes.
Yeah.
Does every equality still hold? Is the leftmost subtree still all smaller than 3.5? And is the rightmost subtree bigger than 3.5?
Yes.
Yes, it is. Let's do the same with the successor and assume that we will pick this successor instead of the predecessor. So that means 4.12. So we will replace 4 with 4.12. And then delete 4.12, which was previously there. Okay. Is this still a binary search tree?
Yes.
Yes. Okay. So this is what we're going to need to do here. Okay. Either find the successor or find the predecessor and simply replace it with our root, with our current root, because again, let's look at the code a bit. Here we go. Because we are in the case in which we have found the root the node which we are wanting to delete. All right, so instead of simply assigning the left or right subtree to a temporary variable, here we're gonna need to get the successor or predecessor, it doesn't matter, of our current root. What do we do afterwards? Anyone?
We free the root and then return temporary.
No.
No.
Actually, no.
We just need to assign the key of the root to the key of temporary.
Yes, exactly. What else? there's one thing which we are missing. Basically, we cannot have the previous successor there. We need to delete it, right?
Yes, so we free the... No. Huh.
Here's the trickiest part.
We free temp.
We don't do anything.
First find the parent of temp.
We don't need the parent of temp.
Okay.
Any more thoughts? Let's think about it a bit and just implement the get successor function. Meanwhile, maybe we will get some more ideas until then. Now, how do we implement this? Any idea? Oh, bummer. Successor. So what is a successor? Think about what I just previously said.
We go one node to the right, then we go as far left as possible.
Yes. So let's first off go one node to the right. So current root, or let's just leave it current, equals to node of right, equals to root of right. And then what was it?
We go as far left as possible.
We go as far left as possible, so we don't know how many steps, so we need a while loop. Current different from null, and current of left does not equal to null as well. And while that is true, current becomes current of left. And then we return current. Okay. Is everything clear why this works? So we first off go to the right subtree and then go as left as possible. Okay? And then return once we reach a node which has no left subtree. This is what no left subtree is translated to in code. Then we return current. Okay. So back here, we need one more line of code. Which one is it?
Return null.
No,
it's just...
It is a recursive call, and it looks like this. Equals to something, but what?
Delete temporary.
And where do we start this delete? Because yes, we are going to delete the temporary key. Remember, we now have gotten the successor. We replaced the current root with the successor, but we still have that successor somewhere in the tree. Okay, let's look at the picture again. So here, and we chose to go for the successor, and we want to delete 4.12. And which is the successor of 4.12? Anyone? 4.25, okay. So we replace 4. Actually, let's go back a bit, and yeah, we chose to delete 4, okay. And we found that the successor is 4.12. And let me copy the code so you can actually look at it while we're discussing it. Ta-da. Okay, now we have actually found this, right? The successor of 4, the successor of 4.12, 4 is 4.12, yeah? And we do this, and that means we replace 4 with 4.12. Fuck, gosh. Why does paint work so badly? All right, and finally, 4.12. And now what is left? There's only one thing left. We need to make sure that this 4.12 gets deleted. Yes. So
we should start the deletion function from the right child of 4.12.
Of the current 4.12, right?
Yeah.
Yes, exactly. Exactly. And let's go back to the code. Here, I simply need to write temp, actually root of right. That's it. And here I would just need to return root, but that's trivial. Whew. So, is everything clear with this delete function?
Yeah.
Once, let's just go and look at what happens next, just so we're sure everything is clear. So again, paint, we're going to replace this with this. Now, once I do this, once I do this thing, what happens? I end up here, right? Again. And well, root isn't null, but what value does root contain? I started from here.
4.5.
4.5, yes. So which branch do I end up going in? I'm guessing this one, right? Because the key I want to delete is 4.12. And 4.12 is smaller than 4.5. So we go here, and then we end up here again. And root is going to be equal to 4.25, correct?
Yeah.
Okay, and then I end up here again. And finally, I reach this. And our root is now 4.12. Our previous one here, which got deleted, which didn't get deleted yet, but got picked as a successor to this. And I finally end up here, correct?
Yes.
And my left subtree is null. Well, my right subtree is null as well, so it doesn't really matter. But what happens here is I basically free it up and return null. And that means that here, when I return, the left subtree of 4.25 will be?
No.
Null, because here I returned null. And everything goes back to normal. So we tie up the links because of this recursive call perfectly until we are done. All right. Is everything clear?
Yes.
Yeah.
Okay, great. Now, as for your homework, you will have to implement the insertion, at least the insertion of an AVL tree. An insertion in an AVL tree is done such that the requirement to have the height of the left subtree at most one difference to the height of the right subtree for every subtree. And I'll give you a link, a helping link with the pseudocode for this. I'm sure it will help you a lot. But yeah, that is going to be your homework. And when you are done with inserting and maybe even deleting from a perfectly balanced binary search tree, then you will have a data structure which will have both inserting and deleting and finding done in O of log n, which is nice. Very efficient. All right. Any questions? Nothing? No? Okay. Well then, that was it from my side. Do you really not have anything to ask me?
Will this lab be uploaded to YouTube afterwards?
Yes, I'll upload it today. Yes, I'll upload everything. And also the code is already on Git, so you'll find it there. Anything else? All right, so I will assume that everyone got everything and there is nothing unclear. Next time, I think we'll be starting off with graphs. I'm hoping that we'll be able to see each other until the end of the semester because we'll have a few tests which we really need to take. And if not, then I'll find some other solution. Don't worry. Stay safe, stay healthy, take care of you, yourselves, and the ones close to you. And until next time, just, yeah, take care. All right, bye-bye.
Bye.
Thank you. Bye.